Okay, let's get started with some more LeetCode, and I will try to keep better track of what I've worked on today and try to be a little bit more systematic. So we're gonna do 3 easies, 3 mediums, and 3 hards. So let's look at the problem list. And we'll find the first easy that we have not done yet. Okay, we have 3 right here. Remove duplicates from sorted array. Okay. Okay, so given an array of numbers sorted in non-decreasing order, it's an interesting way of saying increasing order. I guess it's not necessarily increasing order if 2 cells next to each other are the same. Remove duplicates in place such that each unique element only appears once. The relative order of the elements should be kept the same. So in place means we need to update the exact same array. Consider the number of unique elements in nums to be k. After removing duplicates, return the number of unique elements. Oh, interesting. Return the number of unique elements. It seems like we have to do 2 things then. We need to remove the duplicates in place, and we also have to return the number of unique elements. The first k elements of nums should contain the unique numbers in sorted order. Okay, I see. Okay, so pretty much we will have to say const k, I guess, or let k to keep track, and we're just gonna return k. And basically we need to go through each element, and since they're sorted, we just need to look at the element next to it. If they're the same, then we basically don't need to increment. Instead, we need to swap it with the thing to the right to bring it over. We might actually have to we might have to actually bubble it up all the way to the end. Yeah, I think we have to bubble it up all the way to the end. So I think we can skip the first one. So we do 4. Can we skip the first one? Because in that case, k would be 1. Well, we know that we're going to do a loop. We just don't know how far that loop will go. I wonder if we should call this length, call this nums.length, and we go up to length, and that this would be nums.length. This would be length, and then rather than increment it, we'll decrement it. That way, if we never enter this loop, it will be correct. If we do enter this loop, we're basically finding exceptions, and we're trying to remove elements, essentially. So we can start at 1. And we'll just kind of keep it simple. It should be I minus 1. It should be I. I'll say if A equals B, then we need to take B and put it, just move it all the way to the end. J equals I. I is less than length. J plus plus. And we don't want to go all the way to the end. We just want to say we don't even need to really move. Yeah, we don't really need to move the number to the end. We just need to move all the numbers to the beginning, really. So num sub I, sorry, not I, j, equals nums sub j plus 1. Basically just move everything over. After that, we could say length minus minus, and we can say I minus minus, because now that we've moved everything over 1, we don't need to increment I. So this actually counters out the increment of I. So if we think about the complexity of this, this is big O n squared. This is an easy problem, so we're probably going to end up with n squared, but let's just see if we pass any of the test cases, because that would tell us whether we understand the problem or not. So we're out of memory. So the only way we're out of memory is if there's an infinite loop, because we wrote the wrong variable. Okay, at the very least, it seems like we've understood the problem. We can submit it and see where we end up on the leaderboard. And we did do terribly. Okay, so this is what I'm thinking now. We don't need to move everything over the way that we are. So how do we optimize this? This is n. This is n. So we don't necessarily want to do this bubble every time we find a match. Basically, you want to have like a let insert at 0, and basically we don't do this. The idea is we're keeping track of where we want new unique elements to go. So if A equals B, A is not equal to B, then we'll say nums sub num sub insert at equals. So like the first thing is guaranteed to be unique. So I feel like this should be 1. And this should be B. And if we've inserted, then we need to increment insert at. Else, I think the length decreases. So pretty much if we find a unique thing, then we insert that unique thing at whatever index we're at, increment that index. If it's not unique, we're still gonna go to the next thing, but we're gonna say that we have 1 less item than we used to. So that's an optimization. Let's see if it even works. So we got 1, 1. Oh, and that's because, so we need to see not if it's not equal to or are we inserting the wrong thing? So let's step through it. 1, 1, 2 is nums. Oh, hi Tofu, the Lofu. Yes, I'm coding. How's it going? I hope that you can see me coding. Cool. So it seems like we're pulling in the 1 when we want to pull in the 2. So let's run through this code manually. Length is going to be 3. Insert at is going to be 1. Should this be 0? I think I guess to keep things simple, we could no, because we do -1. We have to do 1. Okay, so I is 1. A is 1 because that's I is 1 minus 1 is 0. Num sub 0 is 1. And then B is also 1. We can invert this logic for now. So is A equal to B? It is. So we just decrement the length. So when we decrement the length, we end up with length 2. And then we go to the beginning here, we do I++, so I becomes 2. Is I less than 3? But now length is 2. Okay, so I think we can still go to nums.length here. And then A will be 1, B will be 2. Are they equal? They are not equal, so we say nums insert at B, or nums insert at is 1, and B is 2, so this would become 2, insert at will become 2, and then we're done. So we can run this, see if we get a good result. We do. We can submit it. So we were at 264 at 5.16%. Should be a lot better. Okay, well, we killed it. So we can get rid of these helpers here. Submit it again if they will allow us. We get 100% again, which is great. Let's look at another person's solution. Okay, so they go through each item. Num sub I equals. So there's like this counter. They're doing something similar. But so they made a certain assumption. Let's see if that is an assumption that I made. Go to description. Okay, so there's always at least one item. So my solution actually considered that there could be 0 items. Their solution does not. If I were to have considered that items are always 1, then yeah, I wouldn't have needed insert at, or sorry, I wouldn't have needed length, and I could have used insert at as the length. So reading the constraints is pretty important in this case. Okay, that's easy. That's one of the easies. So let's go to the problem list. Let's go find our next easy. Remove element. Given an integer array numbers and a integer value, remove all occurrences of val and nums in place. The order of the elements may be changed. Then the number of elements in nums. Then return the number of elements in nums not equal to val. Consider the number not equal to val to be k. You need to do the following: change the number of arrays. This is pretty similar. Pretty similar solution here. So it's just what we're comparing it to is different. And we could look at the constraints again. Okay. We're gonna do this. These should be lets. Nums.length and length. We're gonna go through every element. I++. And pretty much if nums sub I equals val, then we'll say insert at is going to be 0 initially. We might not need length. think what we need is insert at, which we could just call it length, fine. And we'll have an else. I believe we'll have an else. So if the num is equal to the val, we don't want it. So we probably just want to do that. And we'll say nums sub length equals nums sub I. And then we'll say length plus plus. Basically, going through the loop, if we find something that is not the value, the target value, then we're going to insert it into the array. Insert that element into the array at the end of the array, keeping track of length. We're just going to run it. We do pass the test cases, and let's just submit it. This is a big O n algorithm based on the number of elements. And we hit the 100%, which is perfect. You can see what other people have done, and they, interestingly enough, they did a 4 of here. So just, they had, I guess, technically kind of less variables. I feel like their code might actually be, I mean, ours is 0 millisecond, but I feel like their code might be faster. Yeah. Okay. Alright. That was that. I mean, it's a very similar solution, but we'll move on to find the index of the first occurrence of a string. That only took us like 4 minutes. Nice. Okay, we're given 2 strings, needle and haystack. Return the index of the first occurrence of needle and haystack or -1 if not. Obviously we can cheat here. We could just use the existing index function, but that's not really what they're asking us to do here. What we basically need to do instead is we return -1. We have a base case, right? Just assume they did that there is no needle in the haystack. We're gonna do a for loop. We're gonna go through all the letters in haystack. And then all the letters in the needle. Say A is haystack sub I, and B is needle sub J. If they are not equal, then we should break. I don't really like breaks. So what I'm gonna do instead is create another function. Here's haystack, here's needle, here's index, and this for loop will go in here. Basically, we'll do this will go here. I guess we can call this I. This is index. This is I. So if they're not equal, then we'll return false. Otherwise, base case, return true. And then in here we'll do if is same at haystack needle I. Then we'll return I. Unless we have a typo. Output is -1. Interesting. Run it. It's not J. Run it. Okay, so we can't cache it. Yep. So as we go through the needle, we have to go through the haystack too. We can't stay in the same place in the haystack. I'll submit that. Okay, well, we're at 1 millisecond. It's theoretically possible to be at 0 milliseconds, I suppose. I'm curious how many people just called index of. Yeah. So this code is going to be faster than our code just because internally it's likely running on like C level speeds. I think it's kind of lame that people would do this, but I would consider the solutions here probably. Nope. I was gonna say these are more honest, but they're not. This one is more honest for sure. Interesting. Yeah, they do a slice and then compare it to the needle. I don't know why they do this line. They could just return I. So this is like overkill. Like they don't need this variable. They could just put -1. They don't need this line. They could just return I. Let's go here. Okay, so they turn haystack into an array. Find index of needle in array. Wow, they slice and join. But yeah, that seems like it would be really slow. Slicing to get a subarray, rejoining it to get a string, comparing it to the string in its entirety. This is like big O-N, big O-N, big O-N. It's like 3n plus this is another n, so it's like n squared, which our algorithm is n squared too, but there's like 3n in this one inner loop here. And then this one. Technically, if we could have empty strings, and I think that an empty needle is always in a haystack. The empty string is always in a haystack. So I don't know about this. So they created a new variable to keep track of things, and this helped them to avoid doing a second function. What's your favorite topic? I really like doing things with the Canvas API, the HTML5 Canvas API. That's a good question. Thanks for asking, Solaris. I actually made a few videos using the HTML5 Canvas API. I like doing like little drawing experiments. You like trees? Trees are fun. I wish that I could experiment or find a reason to use them. Like in college, you learn about binary search trees, you learn about sorting with trees, and but in practice, in reality, you don't really do it too much. It's already done for you, unfortunately. Yeah. It's good to be able to, you know, find joy in these kinds of things, especially if you're able to utilize it. What's your favorite, what kind of problems do you like solving with trees? Like what tree application is your favorite? I'm assuming you mean, coding trees rather than, correct me if I'm wrong now, but which problem? Yeah, sure. I mean, if there's a LeetCode problem on here, I'm about to do a medium, but I can do another easy. I can skip to a hard. But if you know anything in this list that you want to recommend, I'll definitely take a recommendation. Otherwise, I'm probably gonna do string to integer. Usually hard. If you give me a search, I'll search it. Its own code forces. I don't know if I have. I don't think I've ever heard of that. 5 problems, 2 hours to solve. Ooh. Where's the dark mode? Alright, let's check it. What's going on? Oh, I see. Okay, let me close this. We open this. Oof. Okay, I'm already scared. I see a foreign looking name, instantly makes me scared. The kawaii-ness of a tree. Okay. I don't even know. Baruzbek? I'm not even sure how to say it. Alright. Let me just keep some notes here. Okay, so You received a tree with n nodes. For the chosen root, also find the cuteness. How cute is a tree? Interesting. Consider every set of k distinct nodes of a tree. For each subset, compute its lowest common ancestor. When it's rooted at R, S sub R be the set of distinct roots obtained this way. When cuteness is a tree, then cuteness is a tree where S is the number of distinct elements. After discovering the cuteness of a tree, Marusbeck became interested in finding the kawaiiness of a tree. Kawaiiness defined as the sum of absolute values of the distinct nodes of a tree. Help him by finding the kawaiiness of a tree. Trees connect a graph without cycles. Root the tree special called root. Okay, the first line contains numbers. Number of test cases. First line of each test case contains two integers n and k. 2 is less than k is less than n, less than 2 to the something power. The number of vertices of the tree. Number of vertices of the tree and the number of distinct integers to be chosen. The following n-1 lines describe the tree. Each line contains two integers, u and v. Whew. A part of it is reading the input. Okay, so there's 4 test cases. The first line contains a number of test cases. There's 4. First line of each test case contains two integers, 1, 2, and 2, which is the number of vertices and the number of distinct integers. The following n, where n is the second number, lines, and -1 lines, which is this. Okay. The highlighting helps make it clearer. So is there a way to submit for this? Or do you just like have to create a program at the register? Want to solve the... Oh, this is like competitive? You can copy paste your code. Do they run it? Oh, you have to have an account. Oh, okay. I think like it's not even, the hard part is just trying to understand the problem, let alone doing it. 5, 1, 2, 3, 4, 5, -1, yeah. Describe the tree. Each of the lines contains two integers, u and v. That indicates the edge between vertex u and v is guaranteed that these edges form a tree. I have to understand what u and v are. Yeah, this is a doozy. Okay, I think that I will keep this open, but I will do it later. I think I need to think about it while I do other problems. But thanks for sharing it. I agree that it seems challenging, but I think the hard part is really just understanding the problem and setting it up. It seems like you need to like set up a custom reader and a custom there's a lot of custom code. just to get started. Which is, I guess, why I prefer the LeetCode, because the input is already given. But I will come back to it later. I think in the meantime, I'll just find a medium problem. String the integer a to I. Alright, so implement my a to I, which converts a string to 32-bit signed integer. The algorithm is as follows: white space, ignore any leading white space. Okay, so I could do s equals s dot trim start. I think the other thing is I need to have an account, so I'll make the account probably off stream. S equals s trim start. So ignore any leading white space. Signedness. Determine the sign by checking if the character is minus or positive. The input. Is it just a string of? It's just a string of numbers. Okay. You got another one? Okay. Bearsoft is the biggest IT corporation in Berlin. There are N employees at Barsoft Company, numbered from 1 to N. The first employee is the head of the company and does not have any superiors. Each other employee has exactly one direct superior. The employee X is considered to be superior of the employee Y if the following conditions hold. Employee X is the direct superior of employee Y. Employee X is superior of a direct superior of employee Y. The structure of Bearsoft organized in such a way that the head of the company is superior to every employee. The programming competition is going to be held soon. 2-person teams should be created for this purpose. However, if one employee in the team is superior to another, they are uncomfortable together, so teams of 2 people should be created so that no one is superior to the other. Note that no employee can participate in more than one team. Your task is to calculate the maximum possible number of teams according to... Oh my gosh. Okay, the first line contains the number of test cases, sure. First line of each test case contains single integer, which is the number of employees, okay. Second line contains n minus 1 integers, yes. P, which is the index of the direct superior of the ith employee. Okay, so essentially this guy's direct superior is this guy's direct superior is this guy, and this guy's direct superior is this guy. I think that I'm gonna have to draw something here. So we have this is a tree problem for sure. If I'm understanding this correctly, we have this guy 1, and we have Actually, let's do this. We'll do 0. Do 0. And there's 1. And there's 2. So if we look at this here, 0's direct superior is 1. 1's direct superior is 2. And 2's direct superior is 1? I don't... Okay, I must be not reading this correctly. The second line contains n-1 integers, so there are 3 integers, which is 4 minus 1, there's 3. Where p sub I is the index of the direct superior of the ith. P sub I. P sub 0 is the index of the direct superior. So this guy and this guy have a direct superior of this guy. But this guy has a direct superior of this guy. Where p sub I must not be understanding this correctly. It is, yeah, I mean, I imagine it's a tree, but my understanding is not resulting in a tree. At least not the traditional sense. I don't know if they're... And I don't know if they're using zero-based... Okay, it's not zero-based indexing, which is probably important. So if it's not zero-based indexing, we should do 1, 2, and 3. So the first guy... it still makes no sense. The first guy's superior is himself, then. I think it's the direct superior of 2 is 1. It starts at 2. Oh, because there's 4 employees. So there's some... Oh, p sub 2. Okay. So... Okay. I guess the top guy... There's always some root, it seems. And then there's... p sub 2, whose superior is 1. P sub 3, whose superior is 2. And p sub 4, whose superior is 1. I know that I'm horrible at drawing, but I think that I have drawn this correctly now. And then it's saying that we need to make teams where people don't feel superior to each other. They say that there are 2. What are these? The second line. The sum. This is a second. This is another test case. Okay, this has nothing to do with anything. So the output. Oh, the output is 1. Okay. And the reason I came to that conclusion is because you want to like pull people from different parts of the tree. You want them to basically have a common ancestor, but not... yeah, just be down a different branch, essentially. So like 2 and 4 would go together, or 3 and 4 would go together, but 3 can't be with 2, 2 can't be with 1, 4 can't be with 1, so that's how I got that solution. And we're trying to do pairings of 2. There's probably a little bit more. I could kind of like talk about what I think an algorithm might look like, and it might have something to do with how we probably are going to iterate down each of these, and for each root find like, well, what's the most number of pairings that I can make here? And then for this root, you know, taking what I learned from here and what I can learn from here, what's the most number of pairings that I can make from that, and essentially recursively looking at like lower levels and finding how many pairings. I mean, I guess technically speaking, if there are 2 children nodes, there's already a pairing. And then if this has 2 children nodes, there's already a pairing. But there's also this idea of that a node over here can be paired with a node over here. Something like that. Yeah, I guess like when I recursively go down, I'll see that this has no sibling, so this has no children, so the best this can do is 0. This has no children. It only has 1 child, so the best this can do is 0. But this one has 2 children, so. But then the question is like, how would I detect if there was like another thing here? How would I detect that actually you could pair this guy with this guy, and this guy with this guy? How could I detect that? That would be my question. But yeah, I think like in actuality, the hardest part is probably reading it. Since I kind of understand it, or you can focus on the maximum number of pairs by considering the subtree of some node. Yeah. Why would I do CodePen? So something like this. Is there a run? Okay. So they basically get paired. So the first one is how many? And then we could do dot split. No. Dot map. Line dot split. Space dot map. Large int. Why are we getting not a number? Strange. Okay, so we want some way to kind of figure out how many tests there are, I guess. So equals input sub 0, 0. Just keep a log here. And there are 6 tests. They're all 2-liners, so I'll do for let I equals 0, I is less than tests, I plus plus. That's a called test. And we'll say const employees equals tests sub test times 2 plus 1 sub 0. Not tests, input. Alright, we'll log that. It should be 4, 2, 5, 7, 7, 7. Okay, excellent, that's progress. And then we're gonna have to create rankings. Plus 2. Run it. So, oh yeah, 1, 2, 1. I think that's part of it. And so then we need to actually build the tree. So we need something to keep track of the tree. Trying to think of what would be what's kind of better, I guess. I think like this, it's not a binary tree. I think that a employee can have more than one direct reporter. Which kind of complicates it, I guess. But I think like there's always going to be some kind of tree where we would have like some root node here. As a matter of fact, we could probably do array dot from length employees dot map and create a node for we just need to figure out we don't even care what the the index is at this point. But I think a node can have a parent and it can have children. And so what I'll do is for const ranking in rankings, and just add a function here, add direct report. And we'll say this is a node. So we'll say this dot parent is node, and equals, and then node dot children dot push this. I guess we could put a value. And we'll just do index. And then we'll say console.log no or ranking subs no, tree sub 0. And then add a toString to this return. I'll just keep it very simple. I'll just run it and see what logs we get. Okay. I feel like this should have like tabs. And it'll return I could just put the new line manually. This dot children dot map child dot toString I'll do a interface node. Let's say that the parent is a node or null. Children is an array of node. Add direct report. It's a function that takes a node and returns void. And toString is a function that takes tabs, which is a string, and returns a string. And tabs. This is optional. call a tree node. Okay, run it. Okay. So now for here, we will go through and rank things. So we would have to say, so for each index, that we got to do a little bit more here. Let I 0, I is less than rankings dot length I plus plus. What's this? Okay, and then say const ranking equals ranking sub I, and then tree sub I dot add direct report to be tree sub ranking -1. I think this needs to be +1. Something like that. We do dot join. I don't even know how to join it on. I think it would be a new line. And then the tabs would go here. It's interesting. I mean, it looks correct. Here's 0, 1, 2, and then also under 0 is 3. Yeah. Trying to. This is, yeah, I mean, this is very similar to the drawing that I had. Oh, that's cool. Well, I didn't know that existed. That's cool. Okay, I'm gonna have to create a list of resources here. Thanks for sharing that. Okay, so the hard part, I would say, is out of the way. Now that we kind of have them visualized, we can go through them. Is there any way to clear this? Does this do anything? There's no way it does. Wow, it actually does. That's crazy. Okay, so again, I can see why this is 2 or 1, but for this one, it is 0. Okay, I would have thought it was 0. For this one, I would say it's 1. This. For this one, 3. Okay, 3. So is there... Okay, how about this one? This one is... This is also 3? It is also 3. And then for this one, it's also 3. I wonder if we could write a greedy algorithm to get a solution here. Just find the first person that you can match with. I mean, understanding the problem, I think it's not that it's hard, it's just that the fact that you have to write all this code just to get started is kind of a hindrance to do the problem. Like to me, the whole point of the LeetCode, or the advantage of the LeetCode is you can get right to solving the problem. Whereas this, you need to set up your inputs just to start solving the problem. But at this point, that I would create the actual function that LeetCode would give me, which is like get max pairs of a node. I'll get the max pairs of tree sub 0. This is a node. And then we gotta change the order. Let's just call it a function. That way the order doesn't matter. You don't like this? Tree node. But like, okay, so if you are greedy, yeah, you probably won't be able to do it. Because if you just say, okay, match this with this, match this with this, then you only get 2 and it should have been 3. So to some extent, you want to go deeper. But I think you might want to consider pairing this with a sibling. But not just a sibling, but like a sibling with the most children, the most child depth. Like I would rather take a child. I'd rather match this with something with children. A child of something with children than match this with something without children. So there's something that I should consider, like when I'm looking at the children, who should I match it with? So I'm thinking about this. I could just match it with this, but it would be better if I could like I think right now I'm going to focus on just getting a solution rather than getting an optimal solution. But we can do this, and where did my run button go? Oh, I'm scrolled down too much. Alright, where's this console log? Okay, I feel like it's not console logging is 0 here. Run. What am I doing? Yeah, well, it's not console logging because I didn't call console log. So that makes sense. Okay, so what I'm thinking is I need a couple of functions here. I need get child count, and I need something that like that kind of like pulls a child from the tree. So we'll do get child count, and we'll do return this dot children dot reduce total child total plus child dot get child count this dot children dot length, and then pull child is a little bit more complicated. This is basically gonna like reach as deep as it can, get the lowest child that it can find. That's my idea anyway. I'll let Jan do. Not sure how to say your name, but hello. We'll just say it returns this for now. I don't think we need that. So the idea here is we want to go as deep as possible when we pull a child. I think. I just like thinking the least optimized solution right now. So I think like if this dot children dot length, then we'll do something. Otherwise, if this has no children, then we should be returning this. If it has children, then we need to find which child has the most children and pull from that. Okay. Good to know we're on the right path. And part of pulling, there's extra steps, like actually removing it and collapsing parents and whatnot. So that's what makes this a little bit more complicated. I do let result equals this. Return result. And then we'll do some extra logic to where we actually remove result from parent. So we'll do this dot children dot reduce max child. I know get child count is I would consider it very expensive. Fortunately, these are smaller sets, so I'm not too concerned, but we could consider adding some kind of caching. So we'll do max dot get child count is greater than child dot get child count. If that's the case, then we will continue to use max, otherwise we'll use child. And basically, I guess we could say result equals that. No, we'll say const max equals that. And then we'll say result equals max dot pull child. But then pull child removes the child. Okay, we're gonna have to make something else actually pull the child. Where's get max pairs? Where did I define that here? Find the one with the most children, pull that one's child. Mark that as a result. Basically, if there are no children, then this is the child we're pulling in. Trying to think of like, what other recursive aspects we're missing? Like, should I prioritize going deep first? Maybe I should prioritize going deep first. only problem is if there's only one. How do I go back up? Like these two would get paired, but then how can I pair this with this? Because my concern is if there's a whole bunch, how do I know to go deeper? Like I could try to resolve the children here, and do these are these children more important than the children down here? Like if this had another child, if this is it better to match this with its siblings or to match it with these? I'm thinking basically we only go deeper if we have to, as in we only have one child left. If we have one child, then we'll go deeper. If we don't, if we have more than one child, then we keep making pairs. So essentially it's something like while node dot children dot length is greater than 1. Plus get max pairs of node dot children sub 0. Basically, we make as many pairs as we can at the upper level until we basically can't anymore, and then we have to go deeper. And so I guess in theory, we don't really need to know what has the most children, just what has children. So maybe getting child count is potentially more than we care for at the moment. Yeah, I feel like maybe we don't need to do this. This is probably crazy. And probably get child count is probably crazy. We could probably even simplify this even further. this has children, then pull its first child, otherwise return this. And basically this would be a equals node dot children sub 0 dot pull child const b equals node dot children sub 1 dot pull child. And then we increment pairs, and then we say like a dot remove, b dot remove. And then we just need like a really clean removal algorithm. So pretty much when we remove it, we got to keep in mind that like we will only be removing it because we got all the way down to the point where there were no children. So in reality, it should be like this dot parent dot children dot index of this. If index is not equal to -1, this dot parent dot children dot splice index 1 . We'll do this. Wait on the question marks. It's close. I think we need to say that this returns a number. I'm gonna copy it and paste it somewhere else, just in case there is an infinite loop. I was gonna run it undefined of children. I'm gonna open the debugger, go to console, see if it tells me what line that's at. Okay, not gonna be helpful, I guess. It's this. Something like this. Okay. So 1 1 0 0 1 1 2. Okay, so the 2 is incorrect. 3 and 3. So this 2 is incorrect. But I got like a 90% accuracy. 80 to 90% accuracy. So when we're looking at this, we need to think about Why is it 3? Okay, so I think we are stealing an opportunity for these to match. We're basically saying this to this, this to this, and then there's nothing left for these two. So I guess we can't be greedy, unfortunately. So that makes me think we need to go deeper. We need to go deeper, resolve all the children first. With the keeping open this idea, this option of pulling children if we need them. So yeah, I think that we go deeper first. Something to the effect of const deeper equals node.children.reduce child total child get max pairs node total plus child 0. So yeah, we'll try to go deeper first, and then we'll resolve for this one. All right, so 1, 0, 1, 3. Oh, it's still 2. Interesting. Am I reading this wrong? So 4, 5. Oh. I was reading it wrong. Interesting. Okay, so like I was trying to resolve all this children, but then it only leaves 1 for this. So we need to like I guess we do need a max. Because otherwise actually I don't just how if we pull this child, 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 we pull this child. Why is it only 2? Okay, now I don't understand why it doesn't work. Was this the same one that wasn't working before? Yeah, okay, so we probably do need to do max, because otherwise, what would this get? This would get, it could be match these two and these two, and it would only get 2. So maybe I'm wrong. Maybe we do need to max things. Because this should be 3. We might only be getting lucky in that it works. Because this would match No, these two should match first. Then this should match, then this should match. Because what I'm thinking is really risky. I think there's got to be some kind of consideration that if we're pulling as we go down to pull these child nodes, that there could be a collision of some kind. That something like this is happening, and we should probably be like, oh, whoa, don't pull that. So we should almost consider only pulling things that have no siblings. But there's a chance that that doesn't even happen. There's a chance that everything has a sibling. Yeah, I want to consider potentially, as I iterate down, as I recursive down, that I see this and I was like, oh, don't take these, take this. Okay, I want to see if this is the same thing that's broken, which is 145236. Okay, so in this code, this works, in this code, this works, so. Yeah, so they are switching back and forth. And that's because for this one, it's not good to pair the deeper children, but for this one, it is better to pair the deeper children. Alright, so what if we were thinking about an algorithm where we'll look at a number, see if it only has one child. If it only has one child, we can use that. We can use that number, and then pull these up, essentially. So like if we tried to match this and this, this and this, and then these two would just match. So that kind of complicates the removal. The other question is, which of these two do I prefer? I think I prefer this. This seems like it would be a faster version, so I'll keep this comment in for now. And when I'm determining to pull, I think that the children.length has to be greater than 1. If the children's length is greater than 1, it basically is saying that this element has a pair, and I probably shouldn't take it. But if it doesn't have a pair, then maybe I found its pair. And so when we remove, we got to consider who we have pulled out. And who we have pulled out we need to remove it, but we also need to say this dot parent dot children dot push this dot children. Basically take the children of the current element and make it the children of the parent element, because they are guaranteed superior, not superiors, reports to the parent in that case. Something like that. Okay, so we got 1, 0, 1, 2, 3, 3. Dang. Oh, no, it crashed. Hopefully we didn't lose too much progress. Okay, we did not. So this dot parent dot children splice. Just spliced this dot children on top of it. What is this? I thought splice takes a third argument. What's the issue here? Oh. Can you do like that? Oh, you can't. Okay, there's probably some aspect in which pull child is not pulling anything. Well, let's do... And then we'll do... just kind of something to help us break out of the loop. One, 0, 1. This one is 2. This one is -1. So basically we're trying to, for this, we pull the child, pull the child. We can add more logs, I guess. I thought I put a value. I don't use it. Okay. Oh, we keep doing 5, 3. What the heck? What did I just start logging? Okay. Okay, so curious. Okay, no, not this one. This one we're pulling 5 and 3. We pull 4 and 2, which is fine. Then we pull 1 and 3, which is fine. Then we do 5 and 3. But I already pulled 3. Should be 6. 5 and 6. This parent's children. Splice the index of this in its children. Then add on its children. Let's do this. Let's do log the tree. Oh, we're getting a circular structure. Okay, that certainly means that remove is wrong. Okay. I think 1,000's too high. Even like 20 is probably too high. Even 10 is probably too high. So I'll set the limit to 10. Nice. So we need to think about why what remove is doing. This has a parent, the index of this within its parent. If the index is good, then we're gonna splice at index going by 1 and then add this thing's children to it. Oh, you know what? We don't change the parent of these. We don't change the parent of the children. That might help. Still 2 though. Let's console log less. The 101, it should be 333, but it's 101,233. So let's console log node here. and then we'll run it. Oh, it's still circular. Oh my gosh. It's because I get to call toString. Alright, where's the count 2? Okay, here's the count 2. Okay, so let's do the new line here. Run it again. Count 2. Okay, so we have 0, 1, 2, 5, 6, 3, 4. So let's also do A dot value, B dot value. Run it. And look for count 2. Okay, cool. So first we pull is 1 and 3. Great. That's what we want. Then we pull 2, 5, and 4. Which is, this is 5, this is 4. Great. But then I guess the array's length is only 1. And we shouldn't have pulled 5. We should have pulled 2. We should have pulled 2 and 4. So why didn't we pull 2? Just pulled 1 and 3. This should have. Maybe we have to look at the thing's children. This dot children. Yeah, maybe something to where it's like, okay, if I don't have a sibling, I don't have a pair to go with me. So, now I need to look at this dot parents dot length. Yeah, for sure. So it's like essentially the idea is if I don't have a sibling, then I'm probably not going to be matched with anyone. So I should see if I have siblings. So if this dot parent dot children dot length is 0, then I'll return this. If this dot children dot length, then I'll return children, otherwise I'll return. Okay. So basically has siblings. So 1. if it has siblings. Doesn't have siblings. If it has no siblings, then this is the target. Otherwise, we're going to see if it has children. If it has children, we're going to try to get its child. Because we want to try to find a child that has no siblings. Ideally. I don't know. 101. What? Still 2. Damn. Okay, well. First we pulled 2 and 3, which is great. Actually, I'm surprised we didn't pull 1 and 3. Why didn't we pull 1 and 3? This pulls 5 and 4. Again, why aren't we pulling 1? Like when we children sub-0 pull child, children sub-1 pull child, children sub-0 pull child, we're calling pull child of 1 and the pull child of 4. So when we go to pull child, okay, we're gonna print one more thing. We're going to print just something to verify. Just to make sure 0 is the parent, 0 is the parent, 0 is the parent. Cool. And then for 2, 0 is the parent, 1's the parent, 2's the parent, 0 is the parent, 0 is the parent. Great. 0 is the parent. Oh, but this has a sibling. Okay, so it's under the delusion. It's under the delusion that it could still be paired with this, so it skips it. Interesting. Yeah, for sure. It is interesting. It's gonna be one of those things where I'll never be sure that it's 100% correct, I feel like. Or I'll just randomly get it and it might work in like 99% of cases. What's my solution? Well, I had this idea that I would be looking at to see, like, if this guy has no siblings, then I should consider it highly for a match. But I don't know how to make it so that this one, I feel like I have to say like who I'm looking at. Like if I'm looking at a sibling, then I should probably highly consider another sibling. I know I just said sibling like 4 times, but basically, like, when I pull the child here, but then the order might matter. So basically what I'm saying is I have to pass in A here. Make it so the pull child takes sibling tree node. It's not required. And basically dot filter child it's not equal to sibling. Make this take sibling. And then like pray that it's correct. Damn. Right. So I would have thought that for this second iteration, so for this here, count 2. So 2 and 3 make sense to me because we're just looking at sub 0 and pulling the first child without siblings here, and sub 1 pulling the first child without siblings or without children, which is this. For the next one, I want this to be 1 and 4, so that both of these will pop up and become the roots. So in theory, this A, so the order does matter. I feel like then we have to do like to do that. That. I think if we go recursively, we can skip it. But basically, siblings include child. I don't think this works either, though. Oh, now we still have this 2 here. So for the first one, it's 2, 3, which I would have thought they would have picked 1. So it should be 0. Siblings, oh, it should be not includes. Damn. No, this counts wrong. And that's probably the complete opposite logic that I'm trying to implement here. Yeah, I mean, it should consider taking 1 and 2, but then it takes 4 and 5, which it shouldn't. And the only reason it's doing that is because I'm not sorting it by count. If I sorted it by count, I almost feel like we just need to always sort by count. Maybe this idea of whole child is just a terrible idea. Just always sort by count. Try it. Try to think of why that doesn't work in the meantime. This dot children dot length plus this. Actually, we could just roll that up into the reduce. This dot children dot reduce total child total plus child dot get child count get child count number and for the worst algorithm ever, we'll do no.children.sort no.children nope a b dot get child count minus a dot get child count. One zero one 3 3 3. It works. Alright. It's not efficient in any way, shape, or form. Let me just try to reduce the number of logs. What's this other log? But I got rid of that. Do we even need to do this? Do we even need to go deeper? I don't think we do. Okay, I mean, we have a solution, but I can't prove that it works 100% of the time. 1 0 1 2 3 3. Oh no, I don't have a solution. No. Wait, why don't I have a solution anymore? What's the third one? Why doesn't this get at least one? Oh, because is it because the top tree has nothing? Yeah. Okay. Fine. Fine. Okay. I fixed it. Why are there commas? Very curious. What the heck is the deal here? Why are there commas here? All right. Well, they want a specific output. Okie dokie. 1 0 1 3 3 3. Yeah. I could improve the performance. I could do something where I cache the get child count, or even increment it or decrement it as we add and remove children. But I don't know, caching is risky. So it was a cool challenge. I probably missed an edge case, but that's okay. Thanks for sharing the link, Solaris. Okay, I do need to do a few chores and prepare for a real life interview. I guess technically that's what I've been doing. But yeah, thanks for joining. I'll probably be on tomorrow for more LeetCoding. But I hope that this was helpful and instructive. Yeah, bye for now.